And then the electron jumped from a higher energy to a lower energy level and emitted a beautiful, beautiful photon. And the photon had energy equal to the difference between the energy state levels from which it jumped. And it lived happily ever after without aging due to a consequence of general relativity that while traveling at the speed of light, time doesn't pass. Are you yawning about that? That's exciting. I don't know what you're doing. Oh, good morning. Hey, today I wanted to share with you some physics that you can do in your living room with your pajamas on still. Pretty simple experiment. All you're going to need are a couple of your favorite heavy books. Let's get started. We've talked about translational inertia, or just inertia already. The idea that it's easier to get a light mass, like Sorcerer's Stone, started moving than it is to get a heavier mass, like Deathly Hallows, moving. We can shake this one a lot easier, this is more difficult to shake than this one is, right? So this one resists changes to its motion more. But what if we have a couple of our favorite books here, and we're trying not to shake them back and forth, but just to rotate with them. So try this. Two heavy books right at your chest, and just rotate at your hips. Back and forth, back and forth. In fact, let's go as fast as you can. Back and forth, back and forth, back and forth. Hey, that's pretty good, right? Now do the same thing, but hold the books out at arm's length. Same thing, back and forth as fast as we can. No! Yeah. That's a lot tougher. But why would that be? The mass hasn't changed, so the inertia hasn't changed. This must be something new. This is something we call rotational inertia that depends not only on the masses of the book, but also on where they're placed. Let's look at this in a little more detail. So, let's say that we have this light stick connecting two masses, so like a barbell. And we'll call this mass 1 and mass 2. And I want to spin this whole thing about some axis that goes here. And so that's our axis of rotation. Okay. Then we have each of these masses positioned some distance away from the center. So we'll call this one R1, and this will be R2. If we had more masses, we could include those here as well. And so we might have M3 and R3, M4 and R4. And what we find is that the more mass we add here, so the bigger these things are, the more difficult it is to twirl this. And the farther away they are from the center, the more difficult it is to twirl. And I'm sorry, not from the center, but from the axis about which we're going to rotate this. Now, if you imagine changing this, so I'm not rotating it so these things go in this direction, but maybe I just grab them by the ends here and just try and rotate like this, well, that's quite a bit easier than trying to rotate in this direction. And to demonstrate that, why don't you grab a broom and try spinning it one direction and then just try rotating it like this, and you'll feel that effect very easily. So we find that there's this property that describes how difficult it is to get this thing rotating, or once it's rotating, to stop it. And we call that the rotational inertia. Okay, and the equation for that, I rotational, is equal to the summation of the masses times their distance from that axis of rotation squared. So for this one, I rotational would be equal to M1 times R1 squared plus M2 times R2 squared. Alright, now this works if we have our masses kind of concentrated at one place. We think of these as point masses, all our masses at a single location. But what if we have something that we want to rotate that doesn't really follow that pattern? You know, what if we want to rotate something more like a solid sphere? So we have shading, not my strong suit here. Yeah, that's clearly a sphere, obviously. And then we want to rotate it about some axis that runs right through the middle of this sphere. So it goes right through the center there. Well, then we don't have, just two masses there. We have, well, it's just one mass, but it's spread out. It's got some uniformity to it. So how do we handle that? Well, the good news is we don't have to, actually, because someone else has already done this for us. We handle it with calculus, but we'll just use the effects of that calculus, or the results from that calculus, rather. All these solid objects have well-established moments of inertia or rotational inertias. Those are the same things, just different terms. So we'll just be given a list if you're asked to do any calculations with this. So for example, if we have a long, thin rod with a length L, and we're wanting to rotate it about one end, we have this rotational inertia, ml squared over 3. Or if we want to rotate it about its center, it'd be ml squared over 12. Again, think about that broom. Rotate it about a point around the middle, or swing it right around the end. It's harder to swing around the end than it is to swing it around the middle. So we get a 3 here and a 12 here, a smaller rotational inertia to swing it about its center. So there are big tables of these things. The ones you'll probably see are going to be the long thin rod, or the hollow sphere, or the solid sphere ones. So 2mr squared over 3, 2mr squared over 5 for the spheres. So those are all things that you should expect to see at some point. Then that rotational inertia, that basically takes the place of the mass in a Newton's second law-like equation. So we'll continue with that in our next video. Thanks very much for watching, folks.